All right, good morning. We still got about 3 minutes, and streaming is on already. So for those of you who want to, I guess I'm talking. This is not logical. I should type it, right? Yeah, because people who are planning to go to the YouTube side would not be there already yet. So anyway, I'm just checking out whether my mic is a little bit too loud. It seems that way to me. Nope, it's actually at the same volume as usual. Okay, well, it just kind of sounded kind of loud to me today. Anyway, okay, so that's that. All right. So let me also pre-share the markup or the markdown that I have prepared for today. Because there's some explanation of the problem, the probability problem, with this particular markdown file. So I think some of you may find it useful. And obviously I have to find it first. Where is it? That is the right name. Alright, let me try to find it again. There we go. Alright. We got another minute. So I have pre-shared 2 links and the markdown file. The 2 links, one is going to the lecture material for today, which is Dijkstra's algorithm. The second one is going to a spreadsheet, which is a trace, and this is the actual answer of the homework assignment of the previous semester. Obviously, it's not your solution, but just to let you know, about the format. And then we have the third thing that I just shared in the text channel is a markdown file. And we got about 30 seconds to go, so I'll describe that markdown file in about 30 seconds. So we have exactly 4 classes left. So we got today, this Wednesday, next Monday, and then the next Wednesday. So those are the 4 lectures that we have left, and then we have a final exam in the final week according to the final exam schedule. I believe that we have talked about what day and what time the final is going to be at least once, okay, if not more. So there we go. All right, so it is time to start. I'm going to get started here. The markdown file that is in the text channel is basically me beating the dead horse again. But this time I'm trying to use a different way to explain how we got to the probabilities. So I'm not going to talk about it in class today, but if you do have questions, you can go ahead and use the text channel to ask questions. So I'm not going to talk about it in synchronous mode, but we can talk about this in asynchronous mode. But it's just a different way of looking at the same thing. So we are beating the same horse, the same dead horse, just using a different stick this time. There we go. All right. So now we're going to move on to new business. Okay, the new business is Dijkstra's algorithm. Dijkstra's algorithm is it's not a complicated algorithm. The key is to understand the rationale of how the algorithm is put together. Now, the algorithm that I have, where there's a link in the text channel to it already. So the idea is for you guys to open it separately on your computer. So this way, I can be kind of switching between the algorithm and the spreadsheet, and you can stay on the algorithm on your own computer because you have your own browser open. So that's kind of the idea of why I put the links into the text channel. So you can have one window open to look at the algorithm, which is, I think I put in the correct link to just go straight to the algorithm itself. And then the other link goes to the spreadsheet, which is a trace, and I can see many of you are here already. So this way, it's easier for you guys to follow along because you can look at both the algorithm and the trace at the same time. So when we get to that point, it's going to be handy, but we are not quite there yet. Let me see. You're on an iPad. Even on an iPad, I think you can split screen, right? Because even my cell phone, my smartphone can split screen, so you can potentially split the screen on your iPhone and see if you can look at both pages at the same time. Yeah, you can open both, the Google Sheet and also the web page, and open both of those on a side-by-side basis. I have seen my daughter do it. I don't have an iPad, okay, so I do not do that. I only use my 4K monitor for any real work. So there's that. All right, so here we go. So let's go ahead and explain the algorithm first. Oh, okay, great, excellent. Yeah, it's good to know how to best utilize the tools that you guys have. I now have a cell phone that has a insane resolution. I think it's like 3,000 something pixel by maybe 1,500 or something like that. It's just crazy with a 6.8-inch screen. So the question is, how am I going to utilize all that resolution when my eyes are aging? So the answer is quite simple. I just have to wear one of those loop things, where it can magnify what you're seeing. Yeah, so that's what I'm gonna do. When I need to, use my cell phone as a main source of reading some documents, I'm just gonna put on one of my magnifying, hoods, and those things have they have a prism, which means they help me look at close things, so I don't have to cross eye manually, or not as much anyway. So it helps, it makes looking at things that are close much more comfortable. Yeah, so that's gonna be what I'll be doing, because the phone is also capable of splitting its screen. So yeah, cool. Anyhow, getting back to Dijkstra's algorithm. So with any type of algorithm, it is important to understand what you are given with. Oh, I got a S22 Ultra, so it's the most expensive phone I have ever spent money on. But there are quite a few features that I really like on that phone. So it's I kind of bit the bullet to get that one. Anyway, getting back to here. So the algorithm, you need to understand what you're given with. So these are the pieces that we are in fact given with. There's a G, which is the graph. Okay, so the graph has two components in it. We have to know what the vertices are, and then we have to know what the edges are. Each edge is a two tuple, where the first and the second item are both an element in the set of vertices. We talked about this already. And then we also have a function D. So this is the notation that we say that D is a function, where the domain is the set of edges, and then the codomain is the set of real numbers, but it has to be a set of non-negative real numbers. It can be zero. Okay, zero actually works out okay. It just cannot be negative. So we are mapping each edge to a non-negative real number using the D function, and I chose the letter D for distance. So that's basically why it is named D. And then we have another starting point, which is the set S. S is a subset of V, and this is a subset of vertices identified as destinations. So this is the main difference between the Dijkstra's algorithm that you encounter in CISP430 versus this one. Is the other one, I believe, only has one single destination, whereas this one has multiple destinations, potentially multiple. You need at least one, otherwise it's pointless to run Dijkstra's algorithm. But this particular algorithm can handle multiple destinations. All right, so let's take a pause right now, right? Why do we want to have an algorithm that can deal with multiple destinations? So I'm going to give you a scenario, and I think most people will remember the scenario but not remember the algorithm at the end of today, but that's okay with me because as long as you remember something related to the algorithm, it's still better than nothing. Anyway, so now let's just say that we are at Six Flags, okay, which is the closest theme park to us. So we can compare the route efficiency. Not so much that, okay, but because our objective is to get to only one of the destinations, and all the destinations are considered quote unquote equivalent, which means if you get to any one of these destinations, you are done, okay, you're finished, okay, your task is completed. So just imagine that you are the chaperone, for a bunch of elementary school students and going to Six Flags. Okay, and to me, I know some of you probably really like to be the chaperone in this case. To me, it's a headache. Okay, and because I have done it already. I have done it already twice at least. So anyway, you get to Six Flags, and one of the most common thing that children at that age want to do is to go to the bathroom. So no matter where you are at, some child is going to say, "I need to go to the bathroom." So the question now is, does it matter which bathroom you are going to, accompany the child to go to? It doesn't matter, right? Because a bathroom is a bathroom. So in this particular scenario, all the bathrooms are destinations, and that is the reason why this particular algorithm can take on multiple destinations because they are all equivalent. We just need to find a shortest path to a destination, and we're good. Okay. All right. So several people are typing. No doubt about the scenario that we are imagining that we're in. Grumble, grumble. Six Flags. No, it will always be Marine World, Africa, USA. Yes, I remember that name too. I'm old enough to remember that name as well. Is a destination the head of an edge? No, a destination is just a vertex. That's all it is. It's just that within all the vertices in V, some are designated as a destination. That's all. At this point, we can have a destination that is all on its own and not connected by any edges whatsoever. That's perfectly okay. It's not a problem. So you can have a bathroom on a tiny little island, somewhere, within. I think there's a body of water in the Six Flags. So you have a bathroom that is unreachable, by any means. It's okay. It's still a bathroom. It's just that nobody's going to find a shortest path to that specific bathroom. So we'll talk about all of these. The algorithm doesn't care whether a destination is reachable or not. All right. So if we had two bathrooms that were equal distance from a starting point, then this algorithm will return the set of both of those paths or just one. It just returns one. There's one particular attribute about EPrime. EPrime is always describing a forest. In other words, it is always a single tree or there are multiple trees, but it's not really a general graph. One interesting property of a tree is every node, including the root and all the leaf nodes, okay, and everything in between, there's only one path to it. So EPrime has that characteristic as well. So from any place, you only have one path to a destination. So if there are two destinations equal distance from a single point, the algorithm will only find one of them, and then the other one will not be represented as part of the answer. All right, and at what node does a child ask to use the bathroom? That's a very good question. So if you pop open the map of Six Flags, the nodes are representing all the junctions, all the intersections. Okay, because when you're on a specific path, you don't really have a choice, right? I mean, you cannot just decide, oh, I want to turn this way, or I can want to turn that way, or whatnot. So the nodes or the vertices are representing junctions where you can make a choice. You can choose which way you want to proceed. So those would be our vertices. And you can be anywhere within Six Flags, which means you can be at any vertex within the graph, and then suddenly somebody says, I need to go to the bathroom. And so now the algorithm has to find, quote unquote, the shortest path to a destination. So this algorithm is also interesting in the sense that it finds the shortest path to a destination for every single vertex for the entire graph. In other words, once you run this algorithm, you would have known what is the shortest path to a bathroom. Doesn't matter where you are at in the theme park. So that's also one interesting thing about this algorithm is it finds all shortest paths from every vertex to a destination at the same time. Well, I shouldn't say at the same time because when you run the algorithm, it's obviously somewhat sequential. But when it is done, it would have found the shortest path to a destination, doesn't matter from which vertex. So the solution, which is E prime, now it has V also, but V is kind of common between the problem and the solution. So E prime, which is the a set of all the edges that are in the solution. So E prime is basically forming a tree that will get you from any vertex to the closest destination. All right. So next one, this did remind me of link nodes. And then Mohammed said like on a BST. A binary search tree has a very specific structure to it. A graph in this case, or the solution forest, it's not necessarily a single tree. It can be multiple trees because each each destination is basically becoming the root of a tree. So if you have multiple destinations, you can end up with multiple trees. Let's see. I really like this analogy. It's easy to understand, and it's easy to remember just the analogy, but not what the analogy is for. Yes, I get that a lot too. So when you run the algorithm, are we only looking at one destination at a time? We'll see. Okay, so destinations are not special. Okay, so the idea of coming up with an algorithm is try to make things as general as possible. So the destinations are basically just seeds. Okay, they are a starting point. But once we put them into the initial value of q, we'll get to that later. We don't really care about whether a vertex is a destination or not. Doesn't really change the way we process for the rest of the algorithm. So that's really an interesting aspect of this algorithm too. And when you try to create an algorithm, you really should be thinking in those terms as well. Is try to minimize the consideration of special cases. Turn special cases into non-special cases. That's usually helpful. And you will see in this case, the destinations are not really special. How they're different is how we use them to initialize the things that we need to track. Next one, BST, you have limits on the number of parents. You have limits in terms of the number of children because as the name binary search tree implies, binary means you can only have up to 2 children. Each node can only have up to 2 children. In our terms, okay, each vertex can only have either 2 incoming edges, up to 2 incoming edges, or 2 outgoing edges. Whether it's incoming or outgoing, in terms of BST, it doesn't make any difference, right? Because all you have to do is to say, okay, this side is greater than, this side is less than. So there's no inherent direction to the edges when you're talking about binary search trees. So in a way, it is bidirectional, or you can say it is non-directed. Okay, it's not directed graph. But I understand that when you're talking about Six Flags, it's also the case because most paths are bidirectional. We haven't gotten to the point where in Six Flags, they say, okay, this is one way only. You can go in this direction, which actually does make sense in many cases because when you have a lot of people, moving, having paths that are bidirectional, usually creates unnecessary delays because there are people going in this direction, people going in the opposite direction, and the interface between the directions, has quote unquote friction, and that's when the flow is going to be slower and so on and so forth. So one directional paths are usually more efficient. Anyway, I would assume distance is considered in both situations. Well, distance is just from one vertex to another vertex. And then Luke said one question is forming up in my mind. Oh, okay, I skipped one question, sorry. One question is forming up in my mind, like a bird flies or an actual path that can be taken on ground. It doesn't matter. An edge is representing from one vertex, it's representing the connectivity from one vertex to another vertex. And a vertex in this case is representing a point where you can decide how you want to proceed. So you can be flying, you can be burrowing underground, you can be walking, you can be swimming. It doesn't matter because it's just each vertex is representing a point where you can make a decision, where you can decide which way to go, and an edge is basically specifying the connectivity between those points. All right, and then Chris said better to think of it as cost and not distance. Yeah, well, I mean, I chose the term, distance, because a cost was used, somewhere else. Basically, it's just a number associated with an edge, and you want to optimize and, basically find the shortest path or a path where the total cost distance is the shortest. So from that perspective, Chris, that's why it is called distance, because the term shortest path is well established in literature. So you don't say, if you say it's a cost, then you're looking for the least expensive path. But if you look at d as distance, then the concept of looking for the shortest path in terms of distance, right, still makes sense. So yes, I am splitting hair right now. Yes, I am splitting hair, but I do want to explain why I chose to call d the function, the distance function, instead of the cost function. That's just me completely. That's just entirely me being hair splitting. All right. If this was a routing protocol, the cost would be time for a packet to reach the next router. Exactly. Potentially can also be a cost, if the connection, when you transmit a packet, some company is going to charge the other company some actual money. So anyway, it's just basically you want to find the optimal path. Okay, however you measure the actual cost is up to you. So some of you may have realized that Google Maps, in Google Navigation, you can actually choose between the shortest distance versus shortest time versus the most fuel efficient route. So it has the capability of computing the overall quote unquote distance, which is basically cost or whatever quantity you're trying to optimize to minimize. So you can choose different metrics to minimize. In this algorithm, we just call it distance. Okay. All right. Exactly. Okay, so distance makes sense for people who are more visual because when you look at the map, okay, you're looking at distances, but obviously it doesn't have to be actual distances because a lot of problems that we solve using algorithms like these are not based on maps. Okay, they can be a whole lot of different things, and we're just trying to find the quickest way to do something, and then each vertex is representing a stage of getting that thing done where we can make a choice, and then each edge is representing an action that you can perform, at a particular stage or state. So you're basically trying to find the shortest path, which is basic, or the most optimal way to get something done, given your initial state and where you want to end up, which is the final state. So the final state is considered as a destination in that case, and then each vertex is representing a stage of solving that problem. So, so are we doing okay so far, adequately addressing the first 2 points of what is given to you? You have the graph, you have the distance function, so you know how much each edge is going to cost you, and we also have a subset S of V, so that we know, what vertices are considered destinations. All right, looks like we are good here. All right, cool. All right, excellent. So now, starting with point number 4, we are initializing. In other words, now we're actually doing something that is specific to the problem that is given to us. So we want to do some initialization. So the initialization says here for all v in S. Okay, so that means here we're only considering destination vertices. We define a new function called L. L of v is defined to be 0. So we are associating, the L value of a destination vertex to be 0. All right, so let's pause here, okay, because it's kind of important to understand what L, as a function is representing. L as a function is representing the length of the shortest path known up to a certain point of running the algorithm to a destination from a vertex, whatever the vertex is, in the parameter. That's what L is doing, okay? So let me say that one more time, okay? You might want to jot down the time right now, the actual real time, which is 12:23:27, so you can locate this segment of the recording, easily. So what L is representing is a function. It is mapping a vertex to a real number, and that real number is the length of the shortest known path up to a certain point of running the algorithm. So it is not exactly the length of the shortest path or a shortest path. It is just the length of the shortest path known up to this point of running the algorithm. So it has to be updated as we discover paths. That's what L is representing. So now, understanding that is what L is, this initialization should make sense, right? Because if V is already a destination and we're asking what is the length of the shortest path to a destination, what do you think is going to be the answer? You're already standing next to a bathroom, and then the child said, so how long is it going to take for us to get to a bathroom? What is the answer? Exactly, we are there already. That is why L of v is initialized to 0 for all destination vertices. Are the colons denoting a function? Yes, that's kind of what I said earlier. Oh, you mean this one? No, this one is basically, it's look at this as bad Python. Okay, as a programming language, it's bad Python. Where the colon is. I mean, in Python, you have to use a colon when you specify, okay, this is a loop and what follows is the body of the loop, right? So that's what that colon, this particular colon is serving that purpose. Now, this colon, on the other hand, is designating D is a function. Yeah, I know. It's confusing because we only have so many punctuations in that we use, and sometimes there's an overload issue of, okay, do we mean this or do we mean that? I guess in the future I could have used braces, right? If I use braces, then it resembles C-like languages a little bit better. All right. Yeah, but we're changing the value of L of v, and L is a function. So we are basically just specifying specific elements in V, in L in this case. All right, moving on to the next for each. So the other one is to say, okay, now take a look at the other vertices, all the non-destination vertices. All of those have their L values initialized to infinity because at this point of running this algorithm, we have done zero exploration, which means the best. If I were to ask you, um, okay, so imagine this. Okay, you just got to Six Flags, and a child is already asking you right at the door, "I need to go to the bathroom." Okay, and you haven't even taken a look at the map yet. Okay, and the child is asking you, "So, how long does it take to get to the bathroom?" So you can say you don't know, and or you can, in this algorithm, we say, as far as we know right now, it will take an infinite amount of time because we don't even know whether there are bathrooms in this facility. That's that is why for all the non-destination vertices we say the length of the shortest path to a destination is infinity because we don't even know whether there are destinations in this particular G or not, in this particular graph or not. So there you go. Okay, so are we understanding the rationale of these initializations, to vertices that are destinations and to all the non-destination vertices? Because I think it's really important to understand the rationale. Why are we doing this? Because following the algorithm is mechanical. That's why we have computers. But coming up with the algorithm is not. It's not something done by the computer. So I think it's important to understand the rationale. Why are we doing this? All right. No, this one is not recursive. It is not recursive. All right. Anything else? Looks like we are okay for now. All right. So let's move on. So moving on to bullet point number 5, we have Q, left arrow S. This is the symbol that I use for assignment. In other words, we just take the entire set S, which is the set of all the destination vertices, and say, hey, Q, as a set, this is your beginning value. That's basically what we are trying to do here. We are copying the set S to the set that I call Q over here. So Q is kind of what I would call a boundary set. Basically it is a set where we can say, oh, by the way, some all of these vertices just found a shorter path to a destination. Okay, kind of like that. Okay, that is what Q is representing. Q is a set of vertices where those vertices just got quote unquote updated with a shorter length to a destination. So from that perspective, it does make sense here because we just put zeros into the L function of every single destination vertex. So it kind of makes sense that Q starts with all the elements in S to begin with because we just updated those guys and go like, hey, if you're already here, you're already next to a bathroom. So we know what what is the length of the shortest path to a bathroom from the perspective of those vertices. So that's how we are initializing Q. E prime is initialized to be an empty set. In other words, we're basically saying, hey, we haven't done a single thing. We don't know what edges will be part of shortest paths from vertices to destination vertices. So that's why we are initializing Q and E prime in this particular way. And we're also initializing the L function based on whether it is a destination or not. For every single destination, the L value is a 0. For every non-destination vertex, the L value is going to be infinity to begin with. All right, so I'm going to pause and see if there are questions about the initialization of the algorithm before we proceed to the rest of the algorithm. So if you do have a question or do you want to have some clarification, now would be a good time to ask questions. I gotta press this button. This is partially why I want to go back and teach, face to face. At least I'll be seeing some people nodding and some people frowning and some people just kind of falling asleep. At least I get some feedback, right? All right. So the L values are just additional values that we are keeping track for the duration of the algorithm. That is correct. Nathan, you are correct about that. You can keep the L values around if you want to. If you want to answer the quick question of, hey teacher, how long is it going to take to get to the closest bathroom? Well, that's what the L value is going to be able to answer when you're done with this algorithm. If a child just wants to know, how long is it going to be? Can I hold that long to get to the closest bathroom? Or should we find a, let's just say, alternative way to solving the problem? That's what the L value is. So you can keep it around. I mean, yeah, sure, it doesn't hurt to keep it around, but we don't, usually when we try to find the shortest path, we don't need to find, keep the length of the shortest path around. But, no one is going to say anything if you want to keep that around and just go like, okay, this is kind of like free as a byproduct of running the algorithm. Yes, so the L values will be ETAs on not on each destination. It is the ETA to a destination from every vertex. So I have to make it very clear because it is different. So once again, let me just say that one more time. The L function is telling you the length of the shortest path to a destination from every vertex, or whatever vertex you want to use as your parameter. Is that okay? Does everybody understand that part? All right. Okay. So sounds that way. Cool. Now we move on, and so now we actually start the logic of this program, which is kind of the fun part. So the algorithm starts with a condition that says, if this condition is true, stay in the loop. Okay, this is because it's a while loop. While q does not equal to empty, do the following. In other words, if you have just updated the L value of some vertex and we have not removed that vertex from Q, then we got stuff to consider. Okay, that's basically what this condition is trying to say. So inside the loop, the first thing we do is to select a V as an element of Q such that for all W in Q, L of V is less than or equal to L of W. All right, so this is this is me trying to use for all the quantifier. In this case, it's a universal quantifier. This is me trying to use the universal quantifiers and use that type of notation as much as I can. Okay, because that's a very useful and important notation to understand when you want to describe statements in logic. And guess what a program is? A program really is a whole bunch of logical statements with certain actions that you can specify. So in this case, the short way of looking at this is we are looking for a vertex in Q where the L value is the smallest. That's basically what we are trying to express. But instead of saying that in English, I'm using a quantified statement to express exactly the same thing. Alright, so we have a text here. So at the start of this algorithm, each L of V for each V in Q would be 0. So we can just pick whatever one you want. Yes, you can pick there's no such thing as quote unquote the first one. Remember, Q is a set. And in a set, there's no inherent ordering of things, right? So there's no inherent first, second, last, second to the last. It's just a bag of stuff. You reach your hand into the bag and just grab one thing, right? But in this case, you cannot just grab something. You have to grab one of the things with the least L value. So when you have multiple vertices having quote unquote the least value, you can take any one of those, okay? But just pick one, okay? Doesn't have to be when you run this algorithm again using the same graph and same problem set, you can choose a different one the next time you run the algorithm, okay? Because it should still be correct, okay, regardless of how you make that choice when two vertices in Q have exactly the same L value and they are both less than or equal to everybody else. So Danny is correct in the sense that you can choose whichever one you want as long as there's no vertex has a L value being less than them. Okay, that's the other way to say it. All right, very good. So the explanation here is V has the shortest length to a destination of all of the boundary vertices. It looks the most promising, and this is the reason why Dijkstra's algorithm is also classified as a quote-unquote greedy algorithm. So a greedy algorithm is a misnomer, but nonetheless, that's what literature uses, that term to describe this kind of algorithm. I would call this type of algorithm optimistic. Because that's basically what it is. Okay, it's basically saying, okay, of all of these vertices, we'll pick the one that already has the smallest or the shortest path, okay, the shortest path to a destination. And what we're trying to do in the body of the loop is to say, okay, since we know this vertex, has a very short path to a destination, so we're going to look at all the vertices where they have where they lead to this particular vertex V, because it is likely, okay, that we will go through V and find the shortest path for all of the vertices that connect to vertex V. That is kind of the optimistic part of this algorithm. All right, so this is kind of important. Now, but it's also important to understand that if we don't do this, the algorithm may conclude not finding the shortest path. So it is both making sense from the perspective of, oh yeah, it kind of makes sense that we try to be as optimistic as we want, but at the same time, it is also important because if we don't do this, we can end up not finding the shortest path for some of the vertices. So that's kind of important as well. All right, and we got Mohammed still typing, so I'm gonna wait until he's done, and then we'll move on to bullet point number 2 in the loop. Oh, we are not going to take row. We have not been taking row for some time already, since I can't really drop anyone for not being here during the lecture. But I think that's going to be pretty. It's there are certain words it's just this close to my lips, and they go like, no, let's not say that. So I'll just say that it's more effective. I think it's more effective when people are here, live and being synchronous, so that you guys can ask questions and I can answer those questions like right away. Or if my response is not clear enough, we can just kind of bounce in real time instead of relying on text. Where remember, the communication policy says I have 24 hours to respond. Yeah, so we can only go back and forth 7 times in a week using that specific communication policy, right? But if we do it in real time, everybody can chime in. You guys can all kind of talk about it. Someone can help clarify the question. Somebody can help answer the question in a different way. I think that is the value of having a class. Otherwise, you might as well just try to learn all of this stuff from a textbook, which some of you probably prefer anyway, but that's not how the class is organized. All right. So now we are moving on to the second point. Okay, so the second point here is to change the set Q. So we are basically removing the vertex V from Q at this point. In other words, we are reaching into the set of all the quote-unquote boundary vertices. We say, oh, this guy looks pretty promising. Okay, so we're going to remove that particular vertex from the set and say, now we want to see what vertices are going into this chosen vertex that we put into variable V. All right, and that's the job of this for each loop here. So this for each loop is a nested loop within the while loop. So the for each loop is saying for each e in, and now we have a set notation. I call these ad hoc sets. Basically they don't have a particular name, and we are constructing the set as we go. So in this case, all we are doing here is to filter all the vertices, or excuse me, all the edges in E, and we are only interested in the edges where V is the destination, is the head of the edge. And then we want to consider all the possible tails of edges where the head is the chosen vertex for this iteration of the while loop that we have put into variable v. Alright, so I will pause because I know I just said something that might take some time to digest. In short, we are looking into all the incoming edges to vertex v. Are we good with this, or do you guys need a little bit more time to process that? All right. We're going to test run this algorithm, right? Because, that's part of what I have planned to do for today. So why does removing v from Q expand the boundary? No, it's not that is expanding. The expanding part is done by the for each loop. But once you take a vertex to expand it, then it is no longer part of the boundary because you just expanded the boundary by exploring the incoming edges to v. You can also call Q more or less the unexplored vertices that just got its L value updated. That's kind of what it is. Alright, so I'm not seeing any additional questions. So now we get into the nested for each loop. And then we just say, okay, let's use the local variable e to be wv, which is kind of redundant because that's basically what we have here, to represent e. But this statement here, assume e equals to wv, is actually important because now we know what w is referring to. This w up here, that's only used in order to describe what is in the set that we're trying to describe here. So the scope of this w, the one that is right under my mouse cursor right here, is not going to be visible to the rest of the algorithm. This w, on the other hand, is visible for the rest of this nested control structure. So now we are basically saying, of all of the incoming edges to vertex v, let's just focus on the one where it is coming from w. Now w is just a variable, okay? So we are basically saying, let's focus on one of the incoming edges where we're coming from a vertex, and that vertex is stored in local variable w. So now that we know what e is, now we have a conditional statement to evaluate. So the conditional statement says if L of v plus d of e is less than L of w, then we do blah 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 blah. Alright, so now the question is, what are we looking at here? What is the left-hand side of the comparison versus what is the right-hand side of the comparison? In this case, let's focus on the right-hand side first. What is L of w? What is L representing again? Do you guys remember? It is the length of the shortest path known up to this point of running the algorithm, in this case for vertex w, right? In other words, L of w is simply saying, okay, what is the length of the shortest path to a destination up to this point for vertex w? Okay, it's a particular number. And what about the left-hand side of the comparison? What is that representing? So in order to understand what the left-hand side is representing, it is important to understand that the edge that we are looking at is going from vertex w to vertex v. Okay, so keep that in mind. Now, you can also jot down some notes here to remind yourself that drawing a picture can be helpful. Okay, so I can tell you what the picture should describe, but I can't really I can, but I'm not familiar with Mermaid enough that I can just kind of specify the graph on the fly. But the point is, we are now considering WV as an edge, and an L of V is representing the length of the shortest known path from vertex V to a destination. So when you combine these two, it becomes the length of a path going from W through V to a destination. Are we doing okay so far with that description? This quantity here, L of V plus D of E, is representing the length of a path starting from W and then V and then to a destination. That's what the right hand side of the comparison is representing. So the question is, did we just find a shorter path? In other words, if we get through V from W to a destination, if this sum turns out to be smaller than the length of the current known shortest path from W to a destination, then hey, that's no longer the shortest path because we just found a path where the length is actually shorter. Does that make sense? So let's digest that for now. Why this particular comparison is significant. Because if it is true, it means we just found a shorter path for W by going through vertex V to a destination compared to the shortest path that we found before this. So I'll just kind of shut up and let you guys think about it. Yes, shortest path to any destination. All destinations are considered equivalent. Yeah, we're gonna go through the example. We still got plenty of time. We got about another half hour or so. I think we will be able to get to the spreadsheet. Yep. But I think, yeah, so right now I'm trying to explain the algorithm because the rationale of the algorithm, why a statement is here, why a condition is here, what it is actually representing when it's true, I think that is really important. So let me know when you guys are ready to move on, or if you have any questions about the condition of the if statement where my mouse cursor is located right here. All right. Yeah, EPrime is empty to begin with. It is initialized right before the while loop to be an empty set. Yes, I should have used a left arrow, shouldn't I? Yeah, that was my bad. I mean, that's not consistent of me, and I cannot stand that. Let me fix that. All right, so you guys keep thinking about this condition, and I am just going to go fix that inconsistent thing that I did. And this is module that. All right. There we go. Any questions about this module so far? I mean, about the condition, this condition here. I'm not seeing anything in the text channel. All right, so thanks to Danny spotting this inconsistent use of symbol. I just fixed it here. All right. All right. I thought I saw Philip typing something earlier. Oh, okay. Good. Okay. Excellent. All right. So assuming we're good here, then the next question is, so what if we just found a shorter path? What do we need to do? Well, one of the things we need to do is to say, okay, well, we better update the L value of W because we just found a shorter path. So the length of the shortest path from W to a destination vertex is now updated. So we are replacing an element in the set, okay? Because if you look at a function as a set, we are taking out one element and replacing it with another element so that the value of the length of the shortest path from W is now the length of the shortest path from the shortest known path, okay, the length of the shortest known path from V to a destination plus the distance coming from W to V, because W and V are connected by an edge, and then from from V to a destination, who knows, right? Because V itself can be a destination. It can be going through a really long and windy path. We don't know. I mean, we don't care either, okay? Because all we care is we just found a shorter path from W to a destination by going through V. And then the next one is basically saying, but what if we already stored a path from W, the not so shortest path, is already in E prime. So the first thing we need to do, one thing we need to do here, is to get rid of the edge that we thought was part of the solution, because that turned out to be not such a great idea. So now we look at all the outgoing edges from W. So this U here, this variable U, that is local to just the for each loop. So variable U is not used anywhere else. It's just used in this for each loop. So that we look at all the outgoing edges from W in E prime and just say, hey, we need to get rid of those. Okay. So because we already know that E prime is forming a forest, so we can only have up to one edge coming out of W. So this does not need to be a loop, okay? But it doesn't hurt to be a loop either, because a loop will work when there's only one. When there's none, it will also work when there are multiple edges, outgoing edges from W. But the point is, whatever edges, outgoing edges from W that we have stored in E prime, that's incorrect now because we just found a shorter path, so we need to replace that edge with something else. What we are replacing the edge with is WV, okay? Because WV is how we formulate a path that has a shorter length compared to the shortest path known up to this point from W. That's how we made this comparison true, was we found the path by going from W to V and then V to a destination turned out to be shorter than whatever path that we have found in the prior loop, from the perspective of the while loop. So so this point here is just to add the new edge that should be part of the shortest path known up to this point from W to a destination. But since we just changed the L value of W, W itself is now becoming part of the boundary. It's becoming the unexplored vertex that just got its L value updated. And that's why we need to add W to the set Q. Now I said that, right? So if you just hear what I said, you would have thought about using the plus symbol here and then just a W without the braces here. But we can't do that, okay? There's no such operation, no such set operation to say, let's just add an element to a particular set. At least, not one of the operations that we have described. So the only way we can accomplish that is to use the union operator. But the union operator requires both sides, the left-hand side and the right-hand side, to be a set. So that's why we need the braces around W, because we need to make it a set first before we can apply the union operation. And the union of this becomes the new value of Q. So all we are really doing is we are adding an element of W to the set Q And that concludes the then branch of the conditional statement. There is no else to do because the else is corresponding to, yeah, I can see that you have found another path to go from W to a destination, but it's not any shorter than the one that we have found already. So just can ignore that. That's why there's no else branch corresponding to this conditional statement. All right, that's it, right? I mean, that's basically the entire algorithm because the very last operation here is simply to say, oh, okay, by the way, if you want to look at the solution as its own graph, this is how we construct the solution graph by saying this is a new graph. It has the same vertices as the problem graph itself, but it has a different set of edges. And E prime is guaranteed to be a subset of E because that's because of the process of how we add edges into E prime. So that's why E prime has to be a subset of E. All right. Let's see. Could you explain again, just quickly, what you mean by boundary vertices? So the boundary vertices are vertices where we just found a quote-unquote shorter path from those vertices to a destination. So the idea is that might have changed. Okay, that might have changed what path is shorter from the perspective of vertices that go to the vertices that are currently in Q. Does that make sense? Because okay, so if you think about it as a chain, okay, if you just found a shorter way to do something from one of the one in the middle, don't you think the vertex that is leading up to that vertex might have found a shorter path too? That's basically what Q is representing. Q is representing, hey, we just kind of changed the L values of these vertices, so it is possible that this action, by updating the L value of these vertices, might create a chain reaction so that for other vertices that lead up to one of these vertices, maybe that particular vertex will have found, will find. Okay, that's a better better grammar there. Will find a shorter path as well. That's why we need to keep track of the vertices where the L value just got changed. So that's kind of the best I can explain up to this point, of what Q is representing. All right, Tom is typing something. I'm gonna wait, and the rest of you can kind of take the whole thing and see if you can absorb it, and if not, try to ask questions. All right, I was just wondering if we could see an example. Obviously, yes. Okay, so when everybody is done analyzing the algorithm in a static way, then we're gonna use an example to illustrate the algorithm itself. So the question is, are we ready to move on to the concrete example? All right, looks like we are ready. All right, so what I'm going to do is I am going to drag this to another window, so this way I can see, excuse me. So this way I can look at the algorithm on the side, and we're going to focus on the spreadsheet that is a part of the homework description. So if you go to the tab that says Solution of Fall 2021, that's the one that we are looking at this point. And there's no graphical representation. If any one of you wants to share your hand-drawn is fine, representation, that's fine. But the point is, we should not need that. Okay, I know some of you are very visual, but the point of the algorithm is, we should not be we should not be able to see. Okay, that's bad phrasing there. We should not rely on being able to see the graphical representation in order to follow the algorithm. All right. All right. So this part here is the question. Okay. So this is the question. we have V being defined as a set of A, B, C, D. So there are 4 vertices, and then these are our edges: AB, AD, BC, BD, and then CD. And we also want to define the D function. Now this is where we are going all the way back to looking at a function as a set of 2 tuples, right? So in this case, the first item of a 2 tuple is by itself an edge, which is also a 2 tuple, but for different reasons, because AB is representing an edge, and then AB in parentheses comma 1 is representing the distance of going from A to B using that edge is 1. So now we are defining D as a set of 2 tuples. The graph in this question is G equals to VE, and in this case we have a single destination as vertex D. All right. So that is what is given to us. This is a screenshot, by the way, of that portion of the description. And what we are doing now is to first have to go through initialization. So after all the initialization is done, row 2 is representing the result of having everything done in terms of the initialization. So you can see how I boldface L of D here because it's the only destination. You could do the same thing with the 2 destination vertices for your homework. It just kind of makes it easier to spot the destination. But as I said, the destination is not special after the initialization. So this is just me trying to say, hey, this is special. All right. So now there are other ways to represent L. Okay, I'm just going to spell it out here, but you can probably see why I do not want to use that representation in a trace. Because if you want to look at L itself as a set, because obviously it is, because every function that we talk about in this class can be seen as a set, which is basically the Cartesian product, the subset of the Cartesian product between the domain and the codomain. And in this case, I could have, say L is A infinity, B infinity, C infinity, and then D 0. So I could have used this representation instead of using one column to track each L value of the function. But if I use this approach, it is harder for us to find out, okay, so what is L of C? Well, in this notation, it's pretty easy to spot it. In this notation here, you kind of have to parse the text in order to find out what is the current L value of vertex C. So comparing this representation versus using the 4 columns in this representation, using 1 column per L value is a little bit more clear, and it's just easier for people to track what is the current L value for a particular vertex. So that's the reason why I chose to use this representation instead of this representation here. Yeah, so if you want to use the set representation, that's fine. It's just that's it's not as easy, it's not as visual to most people. And then Danny asked, so if we had 2 destinations, then Q would have contained both of those destination vertices at the start. Yes, so everything that is a destination would be put here, and that has to do with the initialization. Let me just kind of put my code back into this area. So it has to do with this statement here. Q is initialized as S. So we take whatever set S is, and then Q is using it as the initial set, in the initial value of Q. All right. So, yep, triple check, yep, that's fine. All right, so moving on. So that's how the L values are initialized. E prime is easy, right? Because it just gets an empty set. In fact, we just talked about how my notation was inconsistent because I should have used the left arrow to mean assignment throughout, and I used an equal symbol instead. So I fixed that. And then Q is starting with the set of all the destinations, and since we only have one destination, which is vertex D, so Q starts with a single element of D over here. So that's what row 2 is representing, is everything that we do for initialization. And in terms of the algorithm, let me just kind of point out what statements contribute to row 2 of the trace. So that would include everything from here all the way to here. Let me see if I can highlight it. There we go. So all the highlighted stuff here is contributing to row 2, because I really don't see a point of separating row 2 and say, okay, this is how we initialize L, this is how we initialize E prime, and this is how we initialize Q, because all of those initialization can happen in any order. They do not depend on each other. So anything that has no dependency to each other, we can put it all onto one single row, so this way our trace gets a little bit more concise and easier to follow. That's kind of the rationale behind using only one single row to represent all the initializations. Alright, so moving on to row 3. So row 3 is representing how we chose a vertex out of Q and how we remove that particular vertex from Q. So in the algorithm, row 3 is representing the combined effects of these two statements here. The first one to choose what vertex we want to look at, and then the second one to say, okay, since we now have picked out this particular thing to quote unquote expand, let's get it out of the set Q, because it should not be in Q anymore. Is that okay? Does everybody understand what row 3 is corresponding to? Basically, as the result of executing these two statements, we end up with row 3 in the spreadsheet. All right. Cool. All right, so now we're moving on to row 4. So row 4 is representing executing the inner loop, considering the incoming edge to D that we call BD. In other words, in this loop here, we basically say, okay, what about the edge EBD? So this part here is representing the result of executing all of these statements. And as a result of executing those statements, what did we do? Well, we did quite a few things. First of all, this representation does not make it explicit that we state the condition of the conditional statement, but since we updated the L value, okay, so since we updated the L value of B, and we changed E prime, and we also changed Q, so these are indications that the condition was true. Okay, the condition of the if conditional statement was true. This condition here was true. So now, what are the end effects? The end effects are we just found a shorter path from vertex B, which previously did not have a path to a destination. So now we say, hey, by going through D, we can find a path to a destination. Second, did we find a shorter path? Before, the length of the shortest path to a destination was infinity. Now the length of the shortest path to a destination is 3. So yes, we indeed found a shorter path. So as a result of that, we update the L value of B. The W is updated to be simply to denote that we are considering the edge BD at this point. We add BD to the set of solution edges E prime. So technically speaking, there are two steps here. We first have to remove all the outgoing edges in E prime before this, but you can see that E prime was empty, so there's nothing to remove, and then we add the edge of BD. But since B is now getting a new L value, B also has to be added to the set of Q, and that's why we see Q is now including vertex B. So that's basically is representing one iteration of the for each loop. And if you use the text representation, you can see which edge is triggering row 4. It is this particular edge here, BD. We have two other edges going to vertex D. We have CD and we also have AD. So the next one, this particular algorithm decided to explore was CD, which is this particular edge here, CD. So we go through the same motion. Okay, we ask, what is the current L of C? The current L of C is infinity. What about this new path that we find to a destination. What path are we talking about? It is the path of C going through D to a destination. The fact that D itself is a destination is not important, okay? Because all we need to know is, oh, we know there's a path from D to a destination, and the length of that path is 0. That's all we need to understand. So right now, at this point of this algorithm, which one is a destination and which one is not a destination doesn't matter anymore. So, so that particular path, according to the D function, C to D has a distance of 1. So now we know the length of the shortest path from vertex C through vertex D to a destination is 1 plus the L value of D, which is 0. So 1 plus 0 is just 1. And the question now is 1 less than infinity? The answer is yes. So we have to go through all these statements in the then branch of the conditional statement, which is this part over here. So let me just kind of highlight which part I'm talking about. So this is the part that I'm talking about that we're executing now, because the condition of the conditional statement is indeed true. So as a result of that, the first thing we update is L of C, and then we remove all the outgoing edges from C from the current E prime. But you can see that there's nothing outgoing from C from E prime, so we ended up removing nothing. But we do have to add the edge of CD into E prime because it is part of the solution. It's one of the edges of the shortest path known up to this point from vertex C to a destination. But since we just updated the L value of C, we also have to add C to the boundary set. So Q is now including both B and C. So this is the second iteration through the for loop, the nested for loop within the while loop. Now we say, okay, are there any more incoming edges to D? And as it turns out, there's one more, okay, because here's AD. So now we say, okay, A is W, because W is a variable. It is containing the vertex ID for vertex A, and we do exactly the same thing. Okay, so the question is, if we go from A to D, are we going to find a shorter path than what we have discovered up to this point? So let's do the math, right? So the current L value of vertex A is infinity, and the length of the path that we just found is going to be the distance of the edge AD plus the L value of vertex D itself. So we can now see that the edge AD has a distance of 11, right? So 11 plus 0 is 11. The question is 11 less than infinity? The answer is yes, it is less than infinity. So the condition of the conditional statement is true. So we execute the 4 highlighted statements again. But this time, vertex W is A. So by doing that, now we update the L value of A to just 11. And then we remove all the outgoing edges from A from E prime, but since there's none to begin with, we do not end up actually removing anything. But we also have to add the new edge of AD into the set E prime, and because we just updated the L value of A now is part of the set Q also. So at this point, we have run the last iteration of the for each loop. So I'm talking about this for each loop here. So after this, we don't have anything to do within the while loop body. We go back to the beginning of the while loop. We ask the question, is Q empty at this point? The answer is no, it is not empty. It has 3 elements. And then the next thing we need to do, which is represented by line 7, is pick one element out of Q where the L value is the least. Okay, so we look at vertex A. Vertex A has an L value of 11. Vertex B has a L value of 3. Vertex C has an L value of 1. So vertex C is going to be the winner, right? We're going to choose vertex C because it looks the most promising. So that's why, in this particular row in the spreadsheet, it is representing the execution of these 2 statements. so we are basically saying yes, let's choose vertex C as variables v, and also you remove it from Q because now we are considering the incoming edges to C. Now we go to the set of E and we ask what edges are incoming to vertex C. So there's only one that I can see, which is vertex BC. So now we go to here because we now say, okay, now we know which incoming edge we are looking at, which is BC, and W now has a value. But in this case, we are asking also, are we finding a shorter path? Let's see whether we found a shorter path or not. The edge BC has a distance of 2. The L value of C at this point is 1. So 2 plus 1 is 3. That specific 3 is representing the length of going from vertex B through vertex C to a destination. That's what that 3 is representing. The question is, did we find a shorter path from vertex B to a destination? The answer is the current shortest path known up the shortest path known up to this point already has a length of 3. So even though the new path that we just found also has exactly the same length of 3, it's not any shorter. Well, if it's not any shorter, why do I want to go through the then branch of the conditional statement and update a bunch of stuff when it doesn't need to be updated, right? Because we did not find a shorter path. We found another path of the same length. So if it's the same length, there's no need to update anything. That is why on this row here, as we explore the incoming edge of B to C, there's nothing else updated. Okay, none of the L values got updated because we did not find a shorter path for B. And as a result, we don't need to change anything in EPrime, and B does not need to be added back to vertex Q. Now, as it turns out, it's already in vertex Q. Doesn't matter. It does not matter. Okay, we just did not execute anything in the then branch of the conditional statement. I'm just looking at the time. We only got 2 more minutes, but I think we are almost there. So now on this line here, it is representing choose a vertex from Q between vertex A and vertex B. Choose the one that has the smaller L value. So between A and B, you can see vertex A has a L value of 11. Vertex B has an L value of 3. So we choose B, and then we ask the question, do we have any incoming edges to vertex B? So you can see how there's one edge from vertex A to vertex B. That's the only incoming edge to vertex B. So now we go through the math stuff again. We ask, if we go from A to B, it has a distance of 1. And then the length of the shortest path from B to a destination is 3. So we have just found a path with a length of 4. The question is, how does that compare to the length of this shortest path known up to this point? The answer is, well, guess what? It has a length of 11. So we just found a shorter path, and so we have to go through the then branch of the conditional statement, update the L value, take out the outgoing edge from A. So you can see how AD is no longer in EPrime because we took it out. And then we add AB because that is now a part of the shorter path. And we also have to add A back to Q, but since Q already has A in it, it doesn't seem to show because we cannot have 2 A's in a set because they are the same thing. So that concludes the for each loop. And then we go back to the conditional statement, the while loop. And at that point of the while loop, it still has A in it, so we pick out A because there's nothing else left. And then the set Q becomes empty. Now there's nothing after row 11, not because that Q is empty at this point. Because remember, when the while loop executes, when it starts, the set Q still has A in it. It becomes like this because we took A out of it because we still have to go through the while loop one last time. So now we are So there's nothing after that because the graph has no incoming edges to vertex A. So if you look at all the edges here, nothing is going to vertex A, and that is the reason. That's why the for each loop has nothing to do. So when the for each loop has nothing to do, by the time we get back to the while loop, then the set Q is empty, and that is why we got out of the entire algorithm. So the E prime is going to be like this. This is E prime, which is the solution edges, and that is representing the solution. So if you look at these edges, they represent how we get from a particular vertex to a destination. In this case, we only got vertex D as a destination. So let me just add one more thing, and then we are done for today's lecture, because I also have a meeting starting at 1:30. That's why you hear. That's why you're hearing all those beeps. So if you want to go from vertex A to a destination, we go from A to B first, and then from B we go to vertex D, and vertex D is a destination. If you want to start with B, then B goes to D is the shortest path. If you want to go from vertex C, C to D is the shortest path. And if you want to start with D, then the answer is, but you're here already. You're already at a destination. So that's how we found all the shortest paths from a vertex to a destination. Alrighty, so we have we are 2 minutes over time, but I can still answer some short questions, because this is what you're gonna do for your assignment. The assignment is has a 1 week due date, so it's due next Monday at noon. But I'm going to give you a concurrent assignment for A star algorithm. So my advice is think of it as having a due date of Wednesday. So on Wednesday, which is 2 days from now, you'll be done with this assignment and you can focus on the A star algorithm at that point. But I'll give you guys some overlapping time so you have some flexibility of how you want to arrange how you want to get things done. All right. No, I cannot. Well, first of all, we are out of time. And the second thing is it's recorded, right? So all you have to do is to go to YouTube, rewind it back to the time mark. Hopefully you wrote down the time mark of when I started to talk about that. And then just kind of watch that part again. Yeah, so, this is not even visual. This is not even visual because I didn't actually display the graph for this particular in this particular representation, but I did go through. Okay, so if you just look at the set of E, can we figure out the incoming edges to blah, right? And it's really just that. The other thing you can do, okay, for those of you who are looking at this and looking at the assignment and think, oh, but this is really procedural, it's kind of boring and not fun. Okay, if that is not fun for you, you look at this particular solution and your job is to recreate the original graph. And also to come up with the function D and recreate the original graph with E. So that's a little bit more fun because we are looking at the trail of all of the little breadcrumbs by running the algorithm without knowing what the problem looked like to begin with. So I think that could be an interesting exercise for some of you, and doing this is really, I think, is really a good way to study for this class, because in order to reverse engineer, to look at a solution, to go back to say, oh, okay, I think the original problem looks like this, that really requires a good understanding of the algorithm itself, because it has to do with how you interpret all of these little pieces of trails that we left behind as we ran the algorithm. So it's not going to be graded, okay? But I think it's going to be a useful and productive activity if you were to just look at this trail here, the trace here, and then use it to reverse engineer and find out what the original problem might look like. So there is that. All right. So I only got about 4 minutes before my meeting. Any questions from you guys before I get out? It's rewind time. Yeah, I mean, this is the age of Netflix and Hulu and whatnot. I mean, we are all used to that rewind button, right? Pause, rewind. Or you can set up point A and point B and repeat. Yep. Alrighty. All right. Well, thank you. Thank you for hoping that I have a nice meeting. It's a performance review meeting for somebody else, and I think it's going to be a pleasant and short meeting because that somebody else did a really good job. So it's going to be nice. Alrighty. If there are no other questions, I'll see you guys on Wednesday. Bye.